In this lesson, we're going to learn about logistic growth. So, many things in the world that grow, like populations, grow exponentially, or they seem to grow exponentially. However, if populations were to grow exponentially, then they would continue to grow forever and never stop. Well, that's not a reality because things can't grow exponentially. They can't grow indefinitely, which is a good thing because the population of the people population would cover the earth and the galaxy and the universe and would just kind of explode, all right? So the reality is that when things start growing, they start to compete for resources like food, water, money, and parking spaces and things like that. And so the population starts to slow down, all right? And we call this limit that it approaches the carrying capacity. So the growth rate is not proportional in this case just to the current value, but it's proportional to the current value, but it's also proportional to how close the current value is to the carrying capacity. All right? So, quick example, and then we'll dive into the specifics of this. So imagine that we have a rumor spreading through a school of 2,000 students. So the rate that the rumor spreads is directly proportional to both the students who haven't heard, because if there's more students that haven't heard there, well, if you go ask somebody, there's a good chance that they haven't heard and you can tell them the rumor. But it also is proportional to the students who have not heard yet, all right? So how many are left as we approach the 2,000 people? The result is what we call a logistic growth function, all right? So it looks something like this, all right, this graph down here. So as we start off, not many people have heard. So though it's growing quickly because everyone you turn to hasn't heard. And so everybody's telling everyone the rumor and it's growing real fast. But then at some point, people start turning to people and saying, hey, have you heard the rumor? And they say, yep, I've already heard. I've already heard. So there's less people to tell. So the growth rate slows down and it changes, okay? So this is what we call a logistic growth curve, okay? So we have what we call a carrying capacity, mentioned that a moment ago, and we'll call that L because it's a limit. So we can graph this relation or write this equation mathematically like this. The change in y over the change in t, dy dt, is equal to ky. K is some constant there of our growth rate. So k times y times the L minus y. That is the amount of people left over. So y is the amount of people who have heard already, and in this rumor case, and L minus y is how many people are left. So as y gets close to L, notice this value right here will get really small. And eventually this will be pretty much zero. And when this is zero, then the growth rate is zero. It slows down. So the bigger y is, or the closer that y is to L, the rate slows down. All right? So that models the rate of change. And so we're going to solve this, and we're going to use partial fraction decomposition that we've learned a little bit about. And we're going to see if we can get a general solution here, and then we can use that to solve these types of equations. So I'm going to skip those couple examples there. If you want to look at another video, I'll do there for those to jump back to our differential equation here. So here's our differential equation, dy dt equals ky times L minus y. All right, so we want to solve this. So we're going to solve this by integrating. But actually, before we integrate, we need to get all the variables on their own side. We're going to do some separation of variables here. So we can think of this as like over 1. Okay, we're gonna cross multiply, or you can actually just swap these. This is the same as the equation dy over ky L minus y equals dt over 1. Okay, if you want, you can cross multiply and divide, or with proportions, you may know that we can swap diagonally, and the equation is true. Okay, so we're using dy and d here as infinitesimals. Now we can integrate both of these here. And so on the right side, we're going to get t I'm just going to flip sides here. And now we want to integrate this. Well, how do we integrate this? Why don't you write this out? So I'm going to 1 over ky L minus y dy. Okay, well, so for this here, we want to use our partial fraction decomposition. So we're going to say, I wish that I could write this as a over ky plus b over L minus y dy. Okay, well, what do we need to do now? We need to make this into one fraction so it kind of looks like this, leaving the a and the b in there. So let's multiply this by L minus y, and this times L minus y. And this side we're going to multiply by ky and ky. Okay, so what we get is a L minus y plus b ky all over ky times L minus y. And now you'll notice these two equations look similar. So this equation here and this equation, all right, they look similar. The tops have to be, since they are similar, they are equal. Notice our equalities. This is why we put equal signs here. These things are equal. So that means the top of this has to be equal to the top of that. All right, so we could say the top here has to be equal to the top there. So let's work with that now. Let's come back up here. So 1 equals a times L minus y plus b ky. So we want to figure out what the a and the b are here. So we're going to plug in values for y. Maybe like, let's plug in 0. So if that's 0, then 1 equals a times L minus 0, which is L, plus b times 0. And the b times 0 obviously goes away. And we get a is 1 over L. How about if we let y equal L? L is just a constant. So if that's the case, we get a times 0, because we're plugging in L at the top here. And we get b, or plus bkl. That goes away. And so we have 1 equals bkl. Divide both sides by kl. And we get b equals 1 over kl. Now, we found out what a and b are, so we can rewrite this form here as the integral of 1 over L over ky plus 1 over kl over L minus y dy. And, all right, so we're about ready to integrate that. It's a little cleanup. We can move this L downstairs. This is like 1 over LKY. And we can actually take that up front, 1 over LK. And leave that. 1 over Y dy. Plus, move this 1 over LK out. And times the integral of 1 over L minus y dy. And going to use some U substitution here. We're going to end up with some natural logs. So we get 1 over LK times, we can actually just factor that 1 over LK out for the moment, times the natural log of y for the first one. And the next one here, this is L minus y. We need to use a little bit of U substitution. If U is L minus y, then the derivative of L minus y is negative 1. I need a negative here. So we can move a negative out here, which is going to make this a minus integral. Nope. Let's take that integral. So that'll be the natural log of L minus y. Okay. There we go. Now all of this is equal to t. Notice that all these are equal. That's why we put the equal signs there. Okay, that's very important. We can say those are all equal to t. So if we multiply both sides by lk, we have t lk, or lk times k times t, equals the natural log of y minus the natural log of, what is that? That's L minus Y. A little sloppy. Okay. And when we integrated, we should have had a constant here. So let's get a constant of integration up here. Plus C. So we got that plus C also. All right. Let's go move that constant over to the other side. We have LKT minus the constant. And on this right side here, we can rewrite this as a natural log of y, because it's division. Subtraction of logs is equal to division. Something like that. Okay. Now if we take this to the e power here, so we exponentiate both of these here, e to this power, e to this power, we end up with e to the, now this is, when we have an addition like this here, all right, let's call this constant 1 here, all right. When we have an addition like that, that's just e to the LKT, and then times e to the constant. So e to this constant becomes another constant. Okay, if you want to call it C2, you can. Okay. And this becomes y over L minus y. Okay, we're almost there. We're going to go ahead and flip this over, flip both sides of the fraction here. And we got this e to the LKT equals L minus y over y. Why do we do that? Well, let's see. We can rewrite this as, in fact, we're going to just take it to a negative LKT. And this is L over y minus y over y, which is 1. Okay. So this is 1. So let's add 1 to this side and add 1 to this side. We get 1 plus C e to the negative LKT equals L over y. And, well, if we multiply both sides by y and divide by this fraction, we end up with y equals L over 1 plus C. I'm going to drop that 2 for now. E to the negative LKT. And there you have it. That's what we were looking for all along. Okay. So there's our value, and you don't want to go through that again, so it's best to just kind of memorize this. All right, L over 1 plus C e to the negative LKT. That's the form it's going to be. C is a constant. L is the carrying capacity or the limit. And K is just some scale factor. Or more specifically, it would be the growth coefficient there. All right, the coefficient of exponential growth. So one little way to remember that, it's kind of weird, but this looks like LICE, lice minus licked. Okay, lice minus licked. LICE minus licked. LKT. All right, however you want to remember it, that's the idea there. All right, so notice that the carrying capacity L is that top part in that fraction there, and it's also part of the exponent. This is important because that's the limit as it goes to infinity. As t goes to infinity, e to the negative infinity, negative million, negative billion, negative trillion, is very small. So as t blows up, this e part goes away. It becomes 0. And this bottom is just 1. And we're just left with L. Okay? So that's kind of useful to know there, all right? Also useful to see here that it's increasing most rapidly and there's an inflection point at L over 2. You could find that by finding the second derivative, which is the derivative of this, and set that equal to 0. You're going to get L over 2. All right, let's look at a few examples of how this works on the AP exam. So here's a calculator problem. And so we've got the population of Alaska from 1900 to 2000. Can be modeled by the following logistic equation. So here we have the logistic equation. We want to recognize the form. So we have the carrying capacity L over 1 plus 71.57. And that would be the C value. All right, that's just our constant. Doesn't mean too much to us. Times E to the negative, and this would be L times K. All right, T. All right, well, where P is the population in years after 1900. All right, so 0 corresponds to 1900. So we're going to go to our calculator, and we're going to see how this problem works. Okay, so we're going to go to our TI Inspire calculator here, and we're going to start by entering the equation. And this will look a little different because I'm on an iPad here, but same idea as on your handheld calculator. So we're going to go P of T, and we're going to use the colon equals there. All right, that's the store function, and we're going to type in that fraction, 89, 55, 98, divided by 1 plus 71.57 e to the negative, don't forget to use negative, not the minus, 0.0516 t. All right, now I used t, so we've got to use t there. We used t at the beginning, so we've got to continue using t there. All right, so it's stored that in the memory there. Now the first question here, A, is saying what is the predicted population in 2020? Well, that means what is the population? So 2020 minus 1900 would be 120. So that's 120 years after 1900. Okay, so there's our population, 781,218. Now, how fast is a population changing? All right. So now we're going to go back. We need to find the derivative of this. So we're going to go to our calculus. So use control, or actually just menu. Sorry, just menu. And we're going to find our derivative at a certain point. Okay. And we're going to set this up. We use our variable as t. And for starters here, our input value for 1920 is going to be 20. We're finding the first derivative. All that does there is that kind of sets it up for us, all right? So, and what is our function? Well, we've already typed it in there, so we just need to type P of T. There it is, okay? So this is going to find the derivative of P of T at T equals 20, all right? So we hit enter, and there it is. So that's the rate of change at year 20, all right, at 1920. Now, we can do this. We can go up and just do a little pace history because the question has a few of these, and let's just change it. So when t is 40, what is the derivative, the rate of change at 1940? There it is, 4,127 and 79. What is the rate of change at 1999? And there it is. All right, so we can see the rate of change is increasing up to 1999. Well, the question now is, all right, so there we have it for part B. Part C, when was Alaska growing the fastest and what was the population then? Well, we know that the population was growing the fastest when L, the carrying capacity, when the population is half of the carrying capacity. All right. Well, when the what is half of the carrying capacity? Let's see. So let's see. We got 895,598 divided by 2. Okay. So when the population was 447,799, then it was increasing the fastest. The rate of change is increasing the fastest. So that's something we need to know about logistic functions. Okay. So All right, so let's find out when that was happening. So we need to find out. We need to plug that in for our equation. So we need to find out when this P of t here was equal to 447,799. All right, so let's go ahead and solve. So we need to go to menu, solve, or actually menu algebra, solve. Okay, and we're going to solve. We want to find out when P of t, so you don't have to type that whole thing again because we already have P of t typed in. When P of t equals, and I'm just going to go ahead and paste history and grab that, comma. Now we got to tell it what to solve for. We're solving for the variable t. Okay, so you could type this whole thing in there, that whole fraction, and put that equal to 447,000, but we already typed it once. We don't need to type it again. And it will tell us that happens at 82 years, well, in the 82nd year, I guess we could say there, 1982. Okay, so that's when it was growing the fastest. Well, what was the population in 1982 or in year 82? Well, to find the population, we need to go up. I think we're going to need to take this t equals out of here. Now, notice I just used paste history. So we're going to paste history there. Okay, got to get rid of that t equals. And notice it gave me more values than is actually written there. So paste history will give you more exact, and there it is. Okay, yep, that was our population. All right, well, I guess we kind of knew that because we already figured out it was half. That was maybe a little redundant there. Anyways, we verified it for ourselves. That's great. So, okay, last one. What information does the equation tell us about the population of Alaska in the long run? Well, we know it has a maximum will be at 895,598. So that's what it'll approach, and it should max out at that value. So that's the idea of how the logistic function works. Okay, now the AP exam loves to ask you questions to see if you understand the different forms of a logistic function here. So the different forms being this. We have the factored form of the derivative here, ky times L minus y, and we have the function here for y, all right, the population function. So this is the change in the population, and this is the function for the population. These go hand in hand, all right? So they tell us the same thing. Or I guess they tell us about the same function. So one example that shows this here. We got the growth rate of the population of P of bears in a newly established wildlife preserve is modeled by this function here. So here is the derivative function. Notice it's in this here. So we know a couple things. We know K is 0.008. We know that L is 100 because that's in that form. Okay, so the question is this: what is the carrying capacity for the bears in this wildlife preserve? Well, L is 100 bears. Okay, B, what is the bear population when the population is growing the fastest? Well, because we know this is a logistic function, and we know at 100 it has a maximum here, and if we were to graph this, it'll look something like this. So it's going to max out there, and at 50, halfway, logistic functions will always reach their maximum, will be growing the fastest, the maximum rate of change. Okay, so max rate of change is when the population is 50. Now read that carefully. This, what is the bear population? Didn't ask us for time, so we don't need to go solve that for time. Okay, that would probably take a calculator to do best there. C, what is the rate of change of the population? So what's the rate of change when it's growing the fastest? Well, we know that it's changing the fastest when the population is 50, so we need to find d P of dt when the population is 50, so that's 0.008 times 50 times 100 minus 50. And if you punch that into your calculator, you'll get 20 bears per, what's the population here? Or the time? The time is year. Bears per year. Okay, so we should have some units there. All right, there's the idea. Okay, so that's just recognizing the important features of this equation. A couple more good AP problems just to see some different forms of this here. Suppose we have a population that develops according to a logistic differential equation given here, where t is measured in weeks, t is greater than 0. Okay, so notice this is in a little different form. All right, the form we've been looking at has been this: dp dt equals some constant times y, some scale factor times y, I guess we should say, times L minus y. Well, can we get this in this form? Now notice instead of y we have p here. I think we can. So we can factor something out here. If we factor out this 0.002p, so let's factor that out, 0.002p. We're going to pull that out. And so we'll be left with minus p for the second factor, the second term there. And we can divide here. We're going to divide this number by 0.002. And that's just 100. Okay, so there we have it. So dp dt. Okay. So, all right, there's our differential function in a form that looks a little more familiar. So notice here this gives us a maximum L of 100. That's kind of the key there. Okay, so now since we have L there and we have K, we can use our rule to say the solution to this is P equals the carrying capacity over 1 minus some constant that we don't know, e to the negative 100 times, so e to the negative kl or lk, so 100 times this, well that's our 0.2 t. Okay, so well, what's the c all about? Well, it kind of depends on the initial conditions. So this is that constant of integration. So when we solve a differential equation, we get a constant. There's lots of solutions. If we were to graph this, we get a slope field. Okay, and so we can have this. So the question is this: if p0 equals 5, then what is p of t? Well, this works out pretty nice because we can say p of 0, for this is a part A, p of 0 is, well, we know that that's 505, we should say, that's 5 equals 100 over 1 minus c, and that's e to the negative 0.2 times 0. Well, e to negative 0.2 times 0 is just 1, right? So this is 100 over 1 minus c, okay? And so we could solve this a couple different ways. I'm going to use this swap property. When we have proportions, we can swap those diagonally. Did you know that? 1 minus c equals 100 over 5, okay? And so that's 20. And so if we have 1 minus c equals 20, how about if we add c to both sides, subtract 20, we get negative 19 equals c. So our equation here would be p of t equals 100 over 1 plus 19 e to the negative 0.2 t. Okay? So now we'll use that, the same steps there. We'll skip a couple steps there. Okay? We can see there, so here we had the initial value was 5. Well, let's just jump down to here. What if the initial value was 60? All right, so let's skip those first few steps because we'll be the same. 1 minus c equals 100 over 60. Okay, well, this is going to be if we add c, and we'll have 1 minus 100 over 60, that's 10/6, right, equals c. And that's going to be negative 0.667, or negative 2/3. So here, P of t equals 100 over 1 plus 0.667 e to the negative 0.2t. There's our second equation. And last but not least, running out of room here, let's go for c. Let's see, if our initial population here is 120, so 120, plug that in, and we'll jump in midway here. 1 minus c equals 100 over 120. So we could say that 1 minus 100 over 120, well, I'll just write it there. That's 5/6. So 1 minus 5/6 would be 1/6, okay, or 0.1667, all right? So that would give us a population, P of t equals 100 over 1 minus 1667 e to the negative 0.2t. Okay, so last thing here we'll do here is this. Let's sketch it and see what these look like. All right, this is a useful thing to see. So I'm going to go to the graphing calculator and sketch this real quick here. All right, and here's what we get for those 3 graphs. Oh, let's see if we can zoom in there. Okay, here's what we get for those 3 graphs. We get the first one, which had an initial value of 5 here. That's the pink one here. And notice it grows and it maxes out. The second one had initial population of, what was that? That was 60. So it's crossing at 60 here. It looks like we're going by tens. So 60, it comes up and maxes out here. Okay, so it starts here. Okay, so it just went up. Okay, it was always going up and then it slowed down. And the last one, it starts up here at 120, and since the carrying capacity is only 100, the population drops. You see how that works? Kind of interesting. Okay, now ignore all this stuff off to the left, the graph, because t really is only the positive value, all right? So now the last question is this. So there's our graphs. Okay, well, 2 questions. Which one has an inflection point? Well, only this one, the pink one, that had initial population of 5. It was growing rapidly, and there's an inflection point about right here, does it? Now, this green one has an inflection point, but is back here in the negative. So since t can only be positive, it doesn't have an inflection point for the t values we care about. Okay? So which one has an inflection point? Well, that would be the first one with p of 0 equal to 5. All right, and then last but not least, which one is strictly increasing and strictly decreasing? Well, here, this one is strictly decreasing for values. So we'll say strictly, which means it's always decreasing for values greater than 0. And this green one here, this is strictly increasing. Okay, so that gives you a good picture of what's going on with these functions, all right, and how the logistic function works to bring a population either down to that maximum or up to that maximum carrying capacity. And that's what it can look like, because we know that a differential equation is all determined by the initial values. So the particular solution there. So we'll leave it at that because this video is getting a little long there. That gives you an idea of the relationship between the differential equation there and the solution. So we don't have to go through the long steps to find the solution equation because we know that what that solution equation looks like because we're going to memorize it, right? All right. Well, great job. Keep working hard. It's not an easy topic, so don't give up. Thanks a lot.